Okay, this is for page 193 in the Calculus and Vectors textbook, number 12. Write an equation for a function that has a local minimum when x is 2 and a point of inflection when x is 0. Explain how these conditions helped you determine the function. Okay, so let me show you how I did this here. So I need a local min at x being 2. I need a point of inflection at x being 0. So I just tried to make this as easy as possible using some of the information that you guys would have gotten from advanced functions. So if I need a local min at 2, I'm going to put a 0 at 2, and then I can just create an order 2, 0 there that has a local min. If I need a point of inflection, then I chose to do an order 3, 0 at 0, because you can see this is going concave down to concave up, so that's a point of inflection. So I have my point of inflection at 0, using an order 3, 0 from advanced functions, and I have my local min at 2 using an order 2, 0 from advanced functions, and then some more advanced function stuff, then just make a simple function based on that. So here is a function that works. It's not the only one, but it's one that satisfies everything, which is what they've asked for. Okay, next one. Question 13, this says Joshua was sketching the graph of functions f and g. He lost part of his notes, including the equations for the functions. Given the partial information below, sketch the function. Okay, and for part B, it says the polynomial function g has a domain of all real numbers. As x approaches negative infinity, it's going to infinity. G is an odd function. And then it has 5 x-intercepts, 2 of which are for -2, and it goes through the point -1, 5, which is close to a local extremum. The way I did it is I made my own local extremum there, but same kind of idea. Okay, so what I've done here on my handout is I've just kind of wrote down all the specifics that I need, and then I'll talk you through how I actually drew this thing. So first, they said this, I guess they said is close to, so I just drew one in the general area. So here's as good as it's going to get. Sure, I'll do that there. So I put that point in there, and I knew it was some kind of local before I drew anything in, but I knew that point's on the graph. And then they said that I've got x-intercepts at 4, so I put one here, and at -2, so I put one here. Then, how I got the rest of the graph is, they told me that g was odd. So for the function to be odd, that means it's point symmetric about the origin. So to make this as easy as possible, I put a point at the origin, which is going to be one of its x-intercepts. And then if I already had these points here, I need them to be kind of symmetric about that. So if I have one at 4 and at -2, I also put one at -4 and at +2, just so that I can get the symmetry going on with those x-intercepts. And then they said that for this to be odd, if I had a point up here and I needed to be point symmetric here, I just kind of had the reflection of that point across both axes to come down here. And then just to know where to start, they said towards -infinity, this is all going to be up at +infinity. So then I've just kind of connected this through using the information that I put down there. Now everything is going to be satisfied. It's going to go through all real numbers for x. I have that end behavior that's there. It's odd because it's point symmetric about the origin. And I've got 5 x-intercepts. I got one at 4 and one at -2. And then this is close-ish to a local extremum, even though I kind of drew it there. And then this is kind of its counterpart down there.